I finished by talking about this adversarial setting, where you had a number of arms. I said we're going to have k arms, and the adversary chose LTI losses, assigned losses to each of the arms. For each round. And the rounds went on from 1 to up to, let's say, n. And we discussed a very simple algorithm, the exponential weights algorithm. So the exponential weights algorithm computes a weight, and I'm going to write it slightly differently than last time. So you can compute this weight by initially setting it to, I guess I will figure it out on the fly. V0 of I should be set to 1 for I goes from 1 to k, and then you're updating the weights based on the losses that you receive. So at the end of round t, when you receive the loss for each of the arms, or each of the actions, you can update your weights. And so for the next round, if it comes to make a prediction, then you're computing PTI, which is basically VTI, WTI, normalized. Okay? And I of t plus 1 is going to be sampled from this distribution, this discrete distribution. So the probability of IT being equal to I is the same as PTI. Okay, so this was the algorithm that we discussed. And we said that we're interested in the regret of the algorithm. So what's the regret of the algorithm? The regret of the algorithm is the total loss that it suffers compared to the loss that it could have suffered had it known all the losses ahead of time from the beginning of time, and had it chosen the best action, best single action that gives the minimum loss. So if you want to write this out, then you have to first sum the losses that the algorithm suffers, and we're comparing this to the best possible loss in hindsight. And there were two results. One result was that the regret is going to be bounded by square root n times log k divided by 2 for this algorithm. And the other result was that no matter what algorithm you choose, there exists some environment, E, such that the regret of the algorithm against that environment is at least as large as the main term over there, square root n log k divided by 2 plus a lower order term. So it's the same term but a little order term. So this result basically says that you can't do much better in a worst case sense than what this algorithm achieves. Okay. So this is very interesting because we didn't make any assumptions about how the losses are selected. It's kind of like a game theoretic formulation of learning. But you can even go even further. You can go even further. So in this setting, it was assumed that the learner observed the losses for all the arms, even for the arms that it didn't choose. But that is not really a reasonable assumption in many settings. So in many settings, You choose something, and then you get to see its loss or reward, and you're not going to see the loss or rewards for other things that you didn't choose. So for example, it's some very popular example is that you're trying to sell a product on the internet, right? And you put out, I don't know, maybe a bunch of different products, and you're going to sell one of them. So if you sell that product, then you see that like, oh, my customers like the price and the product and everything, but you don't really receive much information about the other products, right? So the action that you choose, you get feedback for that, but you're not going to get feedback for the other actions. So that's the bandit setting, and then you can consider the bandit setting even in this worst case framework. So what is this bandit setting? So the learner only gets LTIT and not the others, not LTI, where I is not equal to IT. So that's the only difference. The game plays the same way. So the adversary selects the losses, the learner makes a choice of what action to execute, send it to the environment, but as a response, the learner can only see the loss of its own action that it selected for a given round. Okay. So can we modify our algorithm, and can we deal with this situation when we have even less information as before? Of course you can. And the trick is very simple. I wouldn't even call it a trick. Probably everyone has seen something similar to this already. Basically, you want to estimate the losses that you haven't seen. So how do we estimate something? You should use likelihood ratios, right? So if you're correct on the average, so the insight here is that if your estimates are correct on the average, then that will be enough for learning purposes. Because in the long run, those averages are going to give you the correct estimates for the sum of the losses. So recall that there is an alternate way of writing these weights. It's the exponent of -8 times the sum of previous losses. So if you have a good idea about the sum of previous losses, then you should be fine. The algorithm is going to work fine. Okay, so we're going to recycle the algorithm. The difference is that we are going to use loss estimates. For each of the actions, we're going to propose some loss estimates. So what is this loss estimate? The loss estimate looks like this. It's going to be really simple. It's going to be the loss that we are going to see divided by the probability that we chose that loss. So this is the loss estimate for the case when IT equals I. You have to divide by the probability to account for that you're choosing the different actions with different probabilities, so that on expectation your estimate is correct. And otherwise, well, you don't have much information, so you're going to use a 0. So that's your loss estimate. So why does this work? So the reason it works is because on expectation this estimate is correct. This loss estimate can also be written as more compactly in the following form. And if I write it in this following form, then you will see why this is correct. So why this is a good idea. So I'm going to use indicator. Okay. So this loss estimate, definitely I can compute this loss estimate based on the information that's available to me, which is IT and LTIT. I didn't see any of the losses. I can compute this. But I can rewrite this loss estimate in this other form with, using this indicator notation. So the indicator with the condition equals 1 when the condition is true and otherwise it's 0, yes. Do you? Okay. Any questions? We're good? Okay. So that's the indicator, right? So it's just 0 or 1. So when it is not equal to 1, then we get the 0, and it doesn't matter that we wrote these unknown quantities there, because 0 multiplied by anything is 0. And when it equals 1, when it equals I, then the indicator is 1. But then, of course, I can replace this I with it, and I can replace that I with it, and I get back this expression over there. So these two are really equal. And if I take the expectation of this latter guy, okay, condition on the past, so PTI, okay, then the expectation of an indicator is just the probability of the underlying event. Okay, so what's the probability that it equals I? P it's PTI. So these two guys are going to cancel. So just to fix the ideas, let me write this. So if I take the expectation of LTI given PTI, then of course this guy comes out, and PTI comes out, and I have to multiply with the expectation of the indicator that it equals I given PTI, which is the same as LTI divided by PTI times PTI. These two guys cancel. So we see that this loss estimate is unbiased on average, or an expectation. Okay, so that's the trick. So know that we have these unbiased loss estimates. We can plug in these loss estimates into the algorithm, and we get an algorithm that just works out of the box. Okay. So this way you get with a few more changes, you get what is called the EXP3 algorithm. That stands for exploration, exploitation, exponential weight. So there is the cube thing, 3 times E. I don't know. It's funny. So this is the algorithm, and there is a few more modifications in the algorithm. So one modification that people usually do is that they're going to induce a little exploration. Okay, so they are going to change the definition of PTI. So PTI used to be just the normalized weights, right? And we're going to keep that mostly, but not entirely. We're going to introduce a little exploration here. So with probability gamma is going to be a number between 0 and 1. And it's typically chosen to be small, and it's on the size of 1 over root t. So with probability gamma, we are choosing an action uniformly at random amongst the actions available to us. And with probability 1 minus gamma, we are just do whatever we did before. So that's the additional exploration. Strictly speaking, the additional exploration is not needed if the losses are non-negative. You can still prove the regret bound that I'm going to talk about for that algorithm. But if you want to prove high probability bounds, for example, then you better include the exploration term where you have negative losses. Then it's again, there is something strange going on with no negative losses. So the exploration doesn't hurt if you are not giving much weight to this uniform exploration. So you see the regret result is that the regret up to time n is square root n. So that means that if the additional regret from a given time step is of the order of 1 over root t at time step t, you are summing up 1 over root t's, that's in the order of root n. So you can afford to explore in proportion to 1 over root t. So that's why you can set gamma to be 1 over root t. That's not a problem. You don't essentially change the regret in that case. Okay? So the other modification that people do, and that leads to a different algorithm. And so just to finish this, and use LT.TI in place of LTI in updating the weights. So since you don't have access to the true losses, you're going to use your estimates. But otherwise, use the same exponential rule. So basically here, you're going to say WTI is WT minus 1I times e to the minus eta L tilde Ti. So that's going to be for EXP3, the update rule. Okay, so the EXP3 point P, that's going to give you high probability bonds, differs by biasing the losses a little bit. So basically, you use the previous estimates, and you also add a beta term. A beta is going to be a tuning parameter that you're going to choose in some fashion, and it's going to bias the loss estimates a little bit, and that is going to have you to reduce the variance. That's the effect of it. Okay, so if you do this, if you run this algorithm, then the following theorem holds. So take EXP3, then the expected regret is upper bounded by essentially ortho square root n times k. And the increase from log k, so this log k was very, very nice to have that. That means that you can deal with huge action sets. You can imagine situations when you're discretizing some continuous set even with many dimensions, and you can still get reasonable regret bonds because you can deal with exponentially large action sets because of the log factor. So that's gone, unfortunately. So instead of the log k, you're going to have a k. That's the big change. Why is that? That's because you're getting information at a much slower rate. Okay? So on average, you're getting like 1 over root k information. So the variance is going to result in that the regret is increased, significantly increased. But at the same time, there is a similar result to what I stated there, that states that, no matter what algorithm you choose, there is an environment such that the expected regret of the algorithm is of this order. Actually here, I should say that's a tilde. There will be a logarithmic term that I'm hiding there. But there is a modification of this algorithm that removes the logarithmic term so that we don't really have a gap between the lower bounds and the upper bounds. Okay. And for EXP3 dot P, it also holds that for all delta, with probability 1 minus delta, the regret is smaller than or equal to some quantity that scales the same, except that there is a log 1 over delta here. So that kind of shows that the regret is going to have a sub-Gaussian tail. So it's kind of like a nicely concentrated regret. So So just the fact that you have log 1 over delta, that's kind of the property of the Gaussian distribution. Okay. So here, I didn't show how to choose, for the sake of saving some time, gamma and beta, but this holds with an appropriate choice of gamma and beta that you can set based on time horizon. Okay, any questions? Good. So one reason I'm talking about this is because later I want to connect to it. And the connection is going to be that you can generalize this framework, especially this part, when we're talking about the full information setting. So you can see that like an alternate viewpoint of looking at this problem is the following. You're playing a game against nature again, and in each time step, it's not a loss vector that nature chooses, but it's a loss function. For each of your choices, there is a loss value. So this goes under the name of online. Usually the loss function is convex, so it's going to be convex optimization. So in online convex optimization, in each round, a loss function is chosen that assigns to each element, let's use the same letter, to your actions. It assigns a real number. Let's say it's a number between 0 and 1. Okay, so that's chosen by the adversary. So this action set, on the other hand, in this case it's not restricted. That's why I started to write T. It's not a finite set anymore. So one example is when A is the k-dimensional simplex. Okay, so you can come through in high dimension, but if you have 3 choices, then you can imagine this property simplex where the corners correspond to the 3 choices, and every point is a convex linear combination of those corners. So this corresponds to a 1, 0, 0 vector. This is the 0, 0, 1 vector. And this is the 0, 1, 0 vector. So this lives in a 3-dimensional space. Yes? So this algorithm, but it's not really the same setting. This solves a more difficult problem, more challenging problem, because it works in the adversarial setting. But the question is absolutely relevant. The expected regret has this rate of growth, square root nk, and UCB achieves the same. And this lower bound actually holds even if the environment is stochastic and stationary. So no algorithm can do anything better even in stochastic stationary environments. So in some sense, you can't do better than this algorithm, but the good news for UCB is that it's achieving the same bound. We'll talk about UCB later a little bit. Okay. The gamma? Or which, when you're not introducing what? The gamma or? Exploration. You will have the same bound. The restriction there is that the losses should be non-negative. It uses a different proof technique that kind of exploits. The proof techniques are very similar. So actually with the exploration, if you just follow the steps of that proof yesterday and you take expectation in the right step, then you will get the result for this one. For this you have to use, for the XP3 you have to use a non-negative martingale argument. But, yeah. Otherwise it's mostly the same, it's the potential function argument. Okay, sorry, where was I? I was here, right? So the online convex optimization framework, every round, the adversary selects a loss function, you have to choose some action. So you're going to choose IT, that's in A. Nothing really changed, right? I just lift the condition that A is finite, and I'm going to say that LT is convex. Okay, but otherwise it's the same game. Yes.
Do you assume A to be convex also? The decision set to be convex also?
And we also assume that decision set is convex. Well, LT couldn't be called convex if A was not convex.
Okay.
Right? So, of course, A is convex. So A has to live, let's say, in RD or some other vector space so you can talk about convexity. Okay? This is a slightly more general framework, but many of the insights from here generalize to this. And actually, this is a special case of this. If you choose the k-dimensional simplex and you choose linear losses, then you basically get this framework, right? Because all your choices can be represented as these special vectors here. And if I allow you to play in a randomized fashion, then you are actually playing within the simplex. Okay? So your choice, your randomized choice is really PTI. So you can imagine that that's your choice. What's your payoff? Your average payoff for that round is going to be just the sum of PTI times LTI, which you can also write as LTP. Okay? I'm just going to use this inner product notation. Okay, so you can see that this is a linear loss. It's convex. It's a very special convex function. So later on, I'm gonna just refer to this, so that's why I put this on. There are many very nice, beautiful results for this setting, but I'm not going to go there today. Okay. So with this, I'd like to switch gears and talk about the stochastic setting. So this was the adversarial setting. What can we do in a stochastic setting? So stochastic finite unbounded. Before I erase everything, any questions? Good. All right. So the finite time setting. So we have k arms, or k actions. Sometimes we call these actions arms because you imagine that you're playing these one-arm bandits in a casino. They have different payoffs, random payoffs. And for each of the arms, so let's say I is an arm, index, there is an unknown underlying distribution, okay, over the reals. So Pi is a distribution over R. If you pull that arm, then you get a random number from this distribution. Okay? So you play this game. It's very similar to the previous one. So in round T, you have to choose an action or arm. Let's the index be IT. And And then, since it's a bandit game, it's similar to this. You got to see the reward from the ice distribution, the distribution that you have chosen. So a reward of, I don't know what letter to use for the reward. If I use R, I use regret for R, and like, I ran out of letters. R is very, very popular. I'm gonna confuse everyone and gonna say that XT is going to be the reward. So you get to see this reward from this distribution. It is this stochastic case. What's the question? Right, it was totally not stochastic. It was adversarial, and right now I should say this is stochastic and stationary. So it's like these things are IIDs. So when I say that this is sampled from this distribution, what I really mean is that this is independent of all previous choices. So you can imagine that like these rewards are sampled for each time step, for each distribution, and you're just selecting one of them, and then you're kind of like back here, except that the rewards are not adversarially selected, or the lossless rewards, doesn't matter, but you're just sampling them from a distribution. Okay. And then you go on. T equals t plus 1, go to 1. So, as usual, we are interested in maximizing the reward, the total reward that we receive. This is this sum. And to evaluate how efficiently we're doing that, we're comparing this. This is going to grow with time, right? So we have to kind of like cancel out the trivial growth. So we have to compare this to how much reward we could have gotten, okay? So it's the other way around. So we could have gotten if we chose okay, so more notation. So let me change this to xtit. So we're going to have this array xti, which is from pi, and t goes from 1 to infinity. And these are all independent of each other. It is not very important that the rewards from different arms are independent of each other, but I just want to simplify here things. Okay. So you have this array, and then here you're just selecting one of the elements from the array. So you can imagine that this array was sampled before of time, and now you're just like picking these elements from the array. Because this allows me to write that, okay, so you're interested in maximizing write this. So what's the maximum expected total reward that we could have achieved? This is just you're summing up the rewards for each of the arms. The expectation take the max. This is what we could have achieved. Rather than achieving this, we only achieved this other amount. And the difference of this is the regret that we are interested in, keeping small. So in the previous case we had losses, we had the two things flipped, but this should still make sense, right? So there is the oracle that knows the distributions, could choose the best action, knowing everything. You're not that, you're going to lose a little bit. The question is how much you lose. most of these guys grow linearly with time. If you're doing your job well, and let's say the rewards are between 0 and 1, right? So if the expected reward is large, so this kind of just normalizes things that you're comparing to the maximum possible achievable total reward. So how do we play in this game? Of course, you could use a previous strategy, and you would achieve that regret bound that's up there on the bound. But you can do actually better. Like that thing doesn't capture everything. So in some sense, in some well-defined sense, you can do better than this. And one of the algorithms that does this is the UCB algorithm. Upper confidence bound, blah, 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 something algorithm. Okay, so how does this algorithm work? It's a very simple algorithm as these other algorithms, similar to these other algorithms. It's going to estimate the rewards, but it doesn't really use the rewards estimate straightforwardly, but it's going to put upper confidence bounds on the rewards. And use the upper confidence bound. So we're going to assume that, for simplicity, that PI is supported on the 0-1 interval. So all the rewards are going to be bounded. So XDI is in 0-1 interval. So whenever you sample, you get a number between 0 and 1. And so the algorithm works by estimating the average reward. So XT I bar is going to denote the estimated average reward that the algorithm can compute. So what's that? So you can so you have all the rewards that you receive, and then of course when you are choosing, so time goes from 1 to t minus 1. So whenever you choose action I, then this reward that you have received, sorry, that's an S, that is the reward that you received corresponds to a reward from a PI distribution. Okay? So you sum up all these and you divide this by how many times you have put this arm. So I'm going to denote this for later reference by TT minus 1I. Okay? So that's the average reward. And to prevent that division by 0, we're going to assume that the algorithm in the first k runs, the k actions, are going to pull each arm once. Okay, so pull each arm once, and so this is going to work for t bigger than k. So this is simple empirical mean for the rewards that you receive for an arm. It's very simple to code it up. So you have the empirical mean, and so I can produce this little plot. So let's say we have like 3 actions, and this is reward. So for the first action, this is our empirical mean. This is x bar t1, and this is going to be x bar t2, and this is x bar t3. So what the algorithm does, is that it's not going to go just by choosing the arm that has the highest empirical mean. It's going to put a bonus term on the top of these means, an upper confidence bound. So basically, it's going to add a well-defined term, a bonus term. Let's call it WT1 for the first guy, and let's call it WT2 for the second guy. Let's call it WT3 for the third guy. To these arms, and if they are unequal, so they are not at the same, there is no tie, then it selects the largest one. If there are ties, then it just selects one of them. Usually there won't be any ties. So what are these bonus terms? So WTI, that's a bonus term. So what are these bonus terms? It is selected in such a way that the probability that, I need some notation, so since we have these distributions pi, we have these samples from pi, what we really care about is the mean reward, right? And I'm going to use the letter mu of I to denote the mean reward for arm I. So that's just the expectation of the reward that comes from arm I for no matter what time step we're talking about. Yes? We don't have what? Can you speak to the mic?
Exponential weight, we have mixed strategy. We found mixed strategy. We use PT there.
Right.
Here we don't have the stochastic
Right.
and
So we are not randomizing. Yes.
We're not randomizing that.
This is not randomized. Yeah.
But we could do better if you do like this, no?
The question is, like, okay, so if you have a stochastic environment, it's not a worst case environment, there is no real need to randomize. The environment is randomizing for you. Right? So the only reason we did the randomization there is because you are in a game situation. Then you really have to randomize, otherwise nothing is going to work. Okay, here you don't really need to do that. Okay, so how is WTI selected? WTI is selected in such a way that the probability that, so basically if you take XTI and you add the bonus term to it, then this with high probability is an upper bound on mu I. So this is larger than equal to mu I with probability, with a large probability. What is a large probability? It's like 1 over 1 minus and t to the power of p, where p is going to be a tuning constant. Okay? So if you know some properties of the distribution, like for example, we know that it's supported on 0, 1, the 0, 1 interval, then you can derive such a high probability. Basically, this is a confidence interval length. Okay? And it's usually going to take a very simple form. So the form that it's going to take is something like this. It's, so there is this term, and usually this is called a delta, right? So you have this log 1 over delta that you have already seen over there. It's kind of like the sign of sub-Gaussianity. So you're going to have log 1 over t to the power of p divided by, and then there is some constant. I happen to remember that in this case the constant is 2 there, but yeah, the constant is not so important. And you divide by the number of times you have pulled that arm, the number of observations that you have for that arm, to be more precise. So if you have more observations, then the width of the confidence interval is going to shrink. Okay, so that's WTI. And so the algorithm itself is going to select the action that maximizes this UCB value. That's the argatum. Okay? Yes?
So I think in the numerator it ought to be log of t to t, not 1 over t.
Yes, because it's 1 over data. It's a good catch. Overcomplicating things. So you have data that's equal to 1 over t to the p. Then 1 over data is going to be t to the p. So that goes into the log. Thank you. So the p comes out and then it becomes a tuning constant. In general, you want to choose p to be high enough so that the total probability that any of the intervals ever fail is small. Okay, so if you make that p really large, like 2 or 3, that would be a large value in this case. I think 2 would do. Then the probability that any time any of the intervals that you ever use is failing altogether, summed up to time t, is going to be of size log n. The sum of the probabilities. So for any given time, it's going to be like 1 over t. You make sure that. And then sum of the 1 over t is just the log n term. And that's going to be small in the regret. That's a small order term in the regret. Okay, so why does this work? So this picture tells you the intuition about why this algorithm is a good algorithm. Okay? So the reason it works is because the algorithm tries to keep the upper bounds the same. If any of the upper bounds is sticking out, then it pulls the arm, and that kind of like pushes down the upper bound. You gain information about that arm, and then the average is moving closer to the estimate, and then this is shrunk. Okay? So in general, there will be an arm that is the best arm. If you run this algorithm and you monitor how it works, then you're going to see a picture like this. So this is a picture proof. So there is the optimal arm. Let's go the optimal arm on 1 with a loss of generality. So that's arm 1. And for arm 1, this is mu 1. And arm 1 is going to be pulled a lot. So the second arm, it's going to have a mean which is smaller than the mean reward for arm 1. So there is a gap between the two, and that gap is called delta 2. And this upper confidence bound, you can imagine that it's really equal to this. And then there is arm 3, and the pattern repeats. So you have the delta 3. So this is going to be roughly at any given time the width of the confidence intervals, because x bar is going to be roughly close to the corresponding mu. It's at least within a distance of w, so I'm hiding a factor of 2 in the w's at most. And the length of this is going to be w2 because the way you are playing this game. Okay? So at any given time, what you can expect is that WTI is going to be of the size of delta I. Okay, and if you solve it, if you solve for t, you plug this in. So you get log t to the p divided by tt minus 1I, and that's equal to delta I. If you solve this for tt minus 1I, so you have to square. That puts a square on delta I squared, on delta I. And you have to take the reciprocal of both sides. You get 1 over delta I squared. And then this went down, so it has to come back. So you have p times log t. then you get this equation that shows how many times you're going to pull each of the suboptimal arms. Okay? So for any suboptimal arm I, the number of times you pull it is going to make these upper confidence bonds equal, and because of that, roughly, this is how many times you're going to pull each of the suboptimal arms. It's logarithmic in t. So you're not really pulling them very often. So that means that you're not losing that much when pulling these arms. In particular, if you are multiplying this by that I, which is the immediate regret that you suffer when you're pulling arm I, immediate expected regret, and you sum up over all arms, then you get this result, which is the bond for this ergatum. So the expected regret, well, there is no need for expectation anymore because the expectations are there. So the regret of UCB is sum of multiply with delta I, one delta I still remains, delta I inverse, log t. And there are some constants that I'm hiding, and you have to sum this for all suboptimal arms. Okay, so if you have an arm which has a smaller gap, you're going to pull it more often, but that's kind of understandable and expected because it's harder to distinguish that arm from the optimal arm than the other arms. And it's increasingly so harder. You have this delta I squared, and because of that, these arms are going to make a larger contribution to the regret. So no, this bond is logarithmic. So you might, oh, sorry, this should be n. So you might expect that, okay, so you might be wondering about like what's going on. Like, didn't I say that you should have a lower bond of size square root n instead of a logarithmic upper bond? Is there a contradiction? There is no contradiction. The reason there is no contradiction is because you can, that's a worst case result. So you fix n, and here I can choose the delta i's in such a mean fashion. There are some other terms that I'm hiding. I can choose the delta i's in such a mean fashion that this will be of the same size as there. Okay, so if I choose delta I to be of size 1 over root n, then this is going to be that big. So now you might be wondering about, does UCB even achieve this bond uniformly over all the environments that we're talking about? And luckily, yes. The answer, maybe not so lucky, it's a good ergatum. So it's going to achieve it, yes. Because what happens is that if a delta I becomes really small, then you shouldn't do the bonding this way. You should just say that, well, I don't care. If delta I is smaller than 1 over root n, then no matter how many times you pull that action during a period of n, the total regret that you suffer because of pulling that action is at most root n. So you don't care. So you divide the arms into two sets, the arms with a very small gap and the arms with a large gap. For the arms with a very small gap, you just use the argument that I taught you. And for the arms with a large gap, you use this other argument. And altogether, you will also see that UCB uniformly satisfies this same bond. Okay. So to complete the picture, I should mention that there is a lower bond that says that the regret for any consistent ergatum for any rich enough environment, any set of rich enough environments, has to grow at least logarithmically. Okay. For any fixed environment within a class of rich set of environments. So that's a different result than this, which says that for any ergatum there exists some environment. So here we are saying fix an environment. In the long run, the regret has to grow for that environment at least logarithmically. How can it be that for every ergatum we can state this? Well, we restrict the set of algorithms to those algorithms that are consistent, which are uniformly fast learning. So that's why you can have such a result. And that result goes back to Loy and Robbins. Okay, what are these linear bandits? So we already saw today that the finite and bandit case for the universal setting could be viewed as an online linear optimization problem. So you had linear loss functions over a simplex. So kind of like, you might think that, okay, then this idea of using linear losses should make sense in a broader context. And this is indeed what we are trying to do right now. So if it generalizes the finite case, it can't be so bad. Must be interesting. Okay. So linear bandits. I'm going to present a version of linear bandits which is a little bit more general than what is usually presented in the literature, but the genetic comes at no price. So I might as well do it, and it's not so much more complicated, but this way, with this more general version, I can capture things which are really interesting practically. So, what are linear bandits? And I'm going to talk about just a stochastic case. You can talk about linear bandits in the adversarial case as well, but today I'm just going to talk about the stochastic case. So you have an unknown parameter vector that you're trying to estimate. I'm going to denote it by theta star. And you have the sequential process, decision-making process. In the round T, you are presented a set. It's a subset of RD, and it's non-empty. But it doesn't need to be convex. It could be a discrete set as well. In many applications, it's going to be discrete. This holds your actions. So the next step you have to choose, and now I'm going to confuse totally, that xt, I'm going to use xt here for your decision. But the reason is going to be clear later. Choose xt. So xt is not the reward right now. The reward is going to be yt. You can do that, right? So you can flip this in your head like it's xt, yt, whatever. Okay. And then finally, you receive a reward. So what's your reward? Here is the assumption. The reward is the inner product of the unknown vector plus some noise. Okay. So you receive reward yt, and we know that yt takes this form. Okay. So eta t here is noise. What do I mean? We're going to assume some very specific property. We're going to say that eta t's are conditionally sub-Gaussian. Okay, so this is about the distribution of eta t. Okay, so I'm making some restriction on the distribution of eta t. So what do I mean by this? I mean specifically the following. If I take, for any lambda real number, if I take eta t to the power of lambda, I compute the expectation of e to the lambda eta t, conditioned on all the previous noise variables and conditioned on all the previous choices, including xt. Then it should be bounded by lambda squared r squared divided by 2. Okay, so this seems like a horrible technical condition, but all what it says is that this noise variable has a nice distribution. This is called sub-Gaussian property, and I'm just making this conditionally true, so I'm relaxing the general sub-Gaussian property. So this means no matter how I select it, no matter what I've seen, this error t is like a Gaussian, just maybe nicer. Like for example, if you have a distribution with a bounded support and zero mean, and the support of the distribution is between minus r and r, then that distribution is going to satisfy this property right away. So if you have such a random variable that is bounded between minus r and r, then you're set. There's a zero mean. Okay. If you have a Gaussian with a variance of r, then again you're set, or r squared. Okay. So this is a very large class of distributions that I allow here. From this property, interestingly, it follows that eta has zero mean. And it also follows that the variance of eta is, conditional variance is smaller than or equal to r squared. Okay, so this is the framework. And as usual, we want to keep the regret small. So what's the regret? So in this case, the regret is a little bit different. So first of all, in each time step, we have a different decision set. So the notion of the optimal action is kind of different a little bit in each time step, right? So when I'm comparing myself to the optimum, then I have to take this into account, that the decision set changes in each time step. So I'm going to just have this. So I'm going to sum from t equals 1 to n of the best decision that I could have gotten in dt, okay, and the reward for that, right? So the mean reward, if I choose some action x, which is this quantity, and this is the best that I could have gotten in time step t. And I'm going to compare whatever I received up to this time to this. Okay, so that's my regret. Well, actually, instead of yt, why don't I write just theta star xt? Basically taking away the randomness of a to t. I will take expectation anyways later, so it doesn't really matter. Okay? But this way, it's a little bit more transparent that we have this, and then instead of this choice, we are choosing this. So this choice could be denoted by xt star. So xt star is argmax of xt of the inner product. Okay, so that's the regret. So why is this linear framework interesting? As I said, it generalizes the finite arm case. It also encompasses the contextual bandit case. So how many of you have heard about the contextual bandit problem? Okay. So let me briefly describe what a contextual bandit problem is. It's a very popular problem because all these internet companies believe that it is the contextual bandit, like if you have a really good solution for that, then that's going to save them a lot of money or generate a lot of revenue. So this display advertising business is like the holy grail for contextual bandit applications. So what is this contextual bandit? In each time step, you receive a context. It's like the customer that's coming to your website. You know a little bit about the customer, like geographic location, IP address, and so on and so forth. Maybe gender, maybe cookies, whatnot, right? Given the customer, you want to put out some ads on your website. And if the customer is going to click on an ad, then you're going to receive some revenue. So finitely many actions, those are the ads that you can put on your website. There's a context that arrives. That's the customer. You know something about the customer. And the value of the action changes based on the context. So for some customers, you want to put up ads about motorbikes. For other customers, it's like, I don't know, beauty products or whatnot, right? So the value of the actions changes radically depending on the customer. So the context, you should have to use the context. Okay. So how do we map contextual bandits to this setting? So let's be clear about this contextual bandits. So you have a set of contexts. And I'm going to talk about the linear version of contextual bandits. So in the linear version of contextual bandits, the following things happen. So first, a context arrives. Then you have to choose one of the actions. And then you receive your payoff. And here I'm going to make the assumption that the payoff depends on the action, the value of the action given the context is encoded by giving different feature values, feature vectors to each of the actions. So for each action, there will be a feature value that depends on the context. And there is an unknown parameter vector. And if you take the inner product of the feature vector with the parameter vector, then that gives you the mean reward. Okay, so there is phi I that assigns to each context a feature vector. And the assumption here is that the mean reward is a linear function of these feature vectors. Okay. So how do we map contextual bandits to the linear framework? We keep the theta star. The only thing that we're going to change is this decision set, dt. Okay. So in a sense, here you can think about that you're not even choosing any of these finitely many actions, but you're choosing one of these feature vectors. And you have finitely many so feature vectors. So if you choose dt to be phi of 1 ct up to phi of k of ct. Okay, so that's your decision set for time t. Then you can model contextual bandits with linear bandits. So linear bandits more general with these changing decision sets. The changing decision sets allows you to encode contexts. Okay. Good. What else can we do with linear bandits? There are many interesting settings. So there is a special case, the combinatorial setting. That's a very, very exciting special case. So what is this combinatorial setting? I want to keep this. So in a combinatorial setting, the decisions that you're going to make are restricted to elements of a hypercube. And somehow with that you can encode a lot of discrete prediction problems. So rather than dt being any set in Rd, if dt is a subset of 0, 1 to the power of d, then we're talking about the combinatorial setting. So what is an example of this? So if you have to select routes in a network, so you have a network, you have a start node, and then you can go to any of the any number of subsequent nodes, and you are doing some kind of routing or something, and you have a target. So you have this graph. So you can send, let's say it is a communication network, you can send packets from the start to the target on different routes, and you have to select routes. Okay. And when you send a packet, then there is some delay, and you learn about the delays. And you want to minimize the delays. The delay is like a loss, right? So it's negative reward. You flip the delay, then you want to maximize the reward. You want to find the path which is the most rewarding in the network. Then you can encode this in this linear framework. How? So D is going to be the number of edges in the graph. And you're going to use the incidence vectors to encode the path in the graph. So each path is going to be just a 0, 1 vector. Okay, it's an element of this hypercube. And since the total delay is the sum of the delays along the different paths, you have this linearity assumption, right? So you have to sum up the individual rewards that correspond to the individual elements. So this maps very nicely to the linear framework. And there are many other problems that similarly like beautiful and have this combinatorial structure and map really nicely to the linear framework. Okay. So sometimes when people talk about these settings, by the way, and they talk about the semi-bandit case too. So what's the semi-bandit case? The semi-bandit case, and it's easy to talk about in the routing problem, is when you not only observe the reward along a path, which is the sum of the individual rewards along each of the edge, but also you receive the rewards along the edges that you selected. So you have more detailed information. So for each decision that you make, if you have a 1 sum entry, you're going to see the corresponding parameter in noise. Okay, so that's the semi-bandit problem. Okay, if you see this in the literature, that's what people mean. And the semi-bandit problem, in terms of its difficulty, is somewhere between the bandit and the full information setting. In the full information setting, that would be the trivial thing and the boring thing where you would receive all the information in every round about all the edges in the network. Okay, so I hope that I convinced you that this is a very interesting class of problems. So how do we learn, how do we play in linear bandits? So I'd like to present a general solution. It kind of like it goes back to the core idea of Loy and Robbins' 1985 paper, where I presented this general idea of that you have to be optimistic in the face of uncertainty. It's called the optimism in the face of uncertainty principle. And the UCB algorithm is derived based on that. You are optimistically evaluating all the arms, and you select the arm which is the best according to your optimistic estimates. When people talk about optimistic estimates, you have to be careful. You're not like unjustly optimistic. You are like very judiciously optimistic about your estimates. So if you have contradictory information, you already know that this arm is pretty bad. You're not going to select it, right? Just being very optimistic. No, it's not working like that. It's like you synthesize all the information that you have, and given that, taking into account the uncertainty that's remaining, that you cannot remove, you're optimistically thinking about the value of each of the actions that you have. Okay, so if you think about this problem, so you have this beautiful linear structure, then how can we apply the optimistic principle here? So we'll need optimistic estimates for the value at each of the actions. What are the actions? The actions are just vectors in this RD space. Okay, so we need optimistic estimates for those. How do we get those optimistic estimates? Well, one way of thinking about this problem is to think about putting a confidence set for theta star, coming up with a confidence set for theta star. If we had a confidence set for theta star that contains theta star with high probability, as you learn more and more, it probably shrinks to theta star. So you're going to have just the right thing, right tool in your hand. So that's indeed what we're going to do. So the general algorithm, which we call the awful algorithm, okay, it's not so bad. Actually, the abbreviation is this: optimism in the face of uncertainty with linear bandits. Awful. It works like this. It requires an oracle that constructs this confidence set. Okay, so the confidence set is going to be Ct minus 1 at round t. So we're at round t. So Ct minus 1 is a subset of Rd which satisfies that the probability that theta is in Ct minus 1 is large. It's something similar to what we have seen before. So the probability that theta star is in the confidence set is this at least 1 minus 1 over t to the power of p. And we'll talk about how we can come along to construct such confidence sets. So once you have that confidence set, the rest is kind of easy. So you're going to choose a theta tilde and an xt, which jointly maximizes the reward. Right. So that's your optimistic choice. We can spell out this choice different ways. So you could say that let UCB of x for a vector x be the maximum for theta being in Ct minus 1 of the inner product between theta and x, and then let xt be the vector within our decision set dt, which gives the best UCB value. Okay, so this is the same choice, right? So it doesn't matter whether you're first finding theta and then finding x, or for each x you first find out the UCB values, you get the same thing. So it's jointly maximizing. The bad news is that this could be hard to solve computationally. And so there is a lot of work going on where you're trying to remove this computational burden or easy it a little bit. And in the commuter setting, there are very interesting questions of like how are you going to scale? How is your computation going to scale with the size of the problem? Anyways, so this is your choice, and that's your XT. Just play XT. Okay. So the question is, does this work? And the next question is, where would the confidence sets come from? So, regarding the confidence sets, there are multiple ways of deriving confidence sets, and we discovered one way by reading a very nice book about self-normalized processes by Victor de la Pana and Shao, and there is, I think, a third author as well. They're presenting a method, an old method, a method of mixtures, and you can apply this to this setting, and you can come up with confidence sets. And I wanted to project something about that, maybe I will try. I just want to show that it makes a big difference how tight your confidence set is. Right. Yeah, so this shows these curves, and this was a confidence set construction that was derived previously in the literature using empirical process theory, and this is the confidence set construction that we came up with based on this old method of mixtures method, and you can see that the difference is huge. And so this is just one example, and there are many examples where it's just much better.
So the DHK is Varshadani, right? Varshadani et al. 2008.
Yeah.
So there they used Martingale thing, Friedman inequality to
That's
come
right.
up with this. What's the fundamental difference that you get a better confidence set here?
So here we are using a completely different technique. This is a method of mixtures technique that I won't be able to talk about today, which is a very beautiful technique. It's kind of like a Bayesian analysis within a frequentist analysis. It's a tricky argument. Yeah. But anyway, so the point is that these methods are pretty sensitive to your confidence set construction. And whether you're going to see good performance or not is totally going to depend on whether you're clever enough in coming up really tight confidence sets. Okay, so this is kind of the Achilles of the method, right? So there are other methods that later we are going to talk about that don't have this problem. So you might see that this could be a problem if it's difficult to derive these tight confidence sets. But at the same time, it's kind of fun to do. That's the algorithm. I can use the third board to try to convince you that this is a good algorithm. As long as your confidence sets are tight. So how do we do this? So we're going to make an assumption that the confidence set, these confidence sets are often of ellipsoid size or ellipsoid shape. Why is that? Well, the reason is because many times they are constructed around the least squares solution. Okay, so you can see that you have basically a least squares problem. You choose covariates xt, and then you see responses which are linearly related. So you can set up least squares problem and get out the least squares solution. Now, if you recall what you learned about least square solutions, typically in statistics, what people consider is that these xt's are fixed, let's say fixed vectors, and the noise is Gaussian. Then basic derivations with Gaussian distribution show that the least square solution is going to have a Gaussian distribution as well, which is centered around the true mean with a certain covariance matrix. Okay, so what's that covariance matrix? So if you do the derivation, then this is what you're going to find. So let's define Vt to be Vt minus 1 to be this sum. Okay, and let's assume that this is invertible. So the least square solution is going to be Vt minus 1 inverse times ys xs, s goes from 1 to t minus 1. And if you assume that ys is theta star xs plus the noise, where eta is, let's say, Gaussian noise, let's say with unit variance for simplicity, then you can plug this expression into the previous expression, and you can see that like you will have a deterministic component. Things cancel out. This cancels the part that comes from the theta. You get a theta star, plus you have a noise component. So theta t can be written as theta star plus Vt minus 1 inverse times the sum of the noises, right? And then this is just the sum of Gaussians, which are independent of each other. So, so the whole thing is going to have a Gaussian distribution. So you're going to see that theta t, minus theta star is going to have a Gaussian distribution with a zero mean, and the covariance happens to be Vt minus 1 inverse. If you do the math, like you have to square, take expectations, independence, cancel things, this is what you get. So this kind of shows you that, well, if you had Gaussians, then you would have like these normal distributions, then it kind of makes sense to talk about ellipsoids. Okay. It also shows that if you take the, okay, so I need some notation. So for a vector x and a positive definite matrix, and by positive definite, I mean a symmetric positive definite, unlike Rich. So this matrix norm is going to be x transpose qx, okay, just very quickly. And so you're going to see that if I take this matrix norm of theta t minus theta star, then on expectation, this is going to be 1 in this case. So it's a constant. Okay. So on an expectation, you can expect the deviation in this norm. And this norm expresses the shape of the ellipsoid to be 1. So because of that, you totally expect nice confidence sets to have this ellipsoid shape, where the shape of the ellipsoid is determined by this matrix. Okay. So this is a quick back of the envelope calculation, and to assume that this is invertible, and that's totally not our case. So maybe in our case, this is not invertible. So you're better off by adding some term that regularizes this sum. Then you're basically doing Ridge regression. And then you can do the same calculations, and then this becomes approximate, but kind of the same things hold. guess I'm totally running out of time, so I don't want to steal time from the lunch. That would be the last thing I wanted to do. So maybe I'm gonna stop here and continue next time with just a short derivation of like how we can get the regret bond for this algorithm by assuming that the confidence set Ct minus 1 is included in an ellipsoid of this shape, of a certain radius. You can expect that the radius is going to be constant because of this. And if that is happening, or it's slowly growing, that radius, then we are going to see that the algorithm is going to have low regret. Okay, and the next time we continue from here, and I'm going to continue talking about other online learning settings, and then finally coming back to a full circle talking about MDP settings, like how these ideas transfer to the MDP setting, and then what can you do, what's known. Okay, thank you.